we're still on exponentials and logarithmic stuff. So in this video, we're solving logarithmic and exponential equations. Let's get started. All right, so what's an exponential equation? An exponential equation is an equation where at least one of the expressions has a variable as an exponent. So here, all right, it could be on both sides. I guess all my examples I have to only on one side, right? Oh, so first method, and this only works some of the time, and when it works, it's really easy. So here, 8 can be written as a exponent of 2, right? So 8 is 2 to the third, so we rewrite it like that. And here, 2 to the third raised to the x is the same thing as 2 to the 3x. Once the bases are the same, you can just ignore the bases and just rewrite it as 3x equals x plus 6. Now this is an easy equation to solve, and just solve it. And let's check it out, see if it works. We want to know if we plug in 3, if those two sides will be the same. Well, 8 to the third is same as 2 to the 9th. So 512 equals 512. Okay. Method 2. This is the more reliable method. Reliable in the sense that you can do it all the time. Alright, so here we have 5 to the x minus 2, and we have this 200. 200 cannot be written as an exponent of 5. So what do? What we're going to do is take the log of both sides. We're taking the log of both sides. One of the convenient properties of logarithms is that you can take an exponent and bring it down, right? It's no longer an exponent. Now, all we got to do is divide by log of 5. Remember, log of 5 is just a number, so we divide by it. And now we just have the x minus 2 left on the left-hand side. We add 2 to both sides, and we have this expression. At this point, we go to the calculator and just plug it in. Now we get a decimal approximation for it, and that's the best we can do for these types of problems. Even when we plug it in, we're going to get this expression, this value, 199.99, and that's close enough for us. Okay. All right. If we need to get closer, we just do more decimal points. More place value. Or it's a Sunday and I can't seem to think straight. All right. That's it. Exponential inequality. I know we've done some inequalities before, but these aren't as bad as those. Okay. Here, you can choose a prize of either a $20,000 car or 1 penny on the first day, and you double that on the second day, and so on and so forth for a month. On what day would you receive more than the value of the car? All right, so this is the inequality, right? It's 2 to the n minus 1 because you're doubling every time. And you want it to be bigger than $20,000. But $20,000 is 2 million pennies. Okay, $20,000 is 2 million pennies. So we want to convert, because here it's in pennies, right? So that's why there seems to be so many zeros here. All right, because we're doing it in pennies. All right, so we take the log of both sides, because 2 million cannot be written as a exponent of 2. We're bringing down that exponent of n minus 1. We divide by the log of 2, and by the way, log 2 million divided by log 2, the 2's don't cancel. All right, and we're bringing the 1 over, and so this equation, this inequality says that n has to be greater than this value. Well, that value is 21.93. Okay, so on the 22nd or 23rd day, you will receive value equivalent to the car, and it's at $28,971.50. That's at day 22. Day 22, you get them 20. All right, so you should. So you have 8 more days to double that amount. So you should go for the penny. Anyway, all right. But my point here is, even though it was an inequality, you just solve it like an equation. Okay, we're not going to do anything weird. When you take the log of both sides, the inequality does not change directions. So you can just solve it like it's a regular equation. Just leave the inequality in there. All right, just in case you have to divide by negative, but in this case, none of that happened. So it should be a relatively straightforward problem to solve, not like some of the other inequalities we've had. Okay. All right. How about solving a logarithmic equation? All right. So when we solve a logarithmic equation, what we're going to do is use the definition of a log. What I mean by using the definition, you're going to take this base and raise it to that power equals that. In other words, we're going to do a basic rewrite. We're going to say 3 to the second equals x minus 5. Well, 3 to the second is 9. Solve this like normal. You get x equals 14. Now, with these problems, you should check to see if the answers work. Generally, when it's simple like this, it'll work, but you can do this mentally. You just plug in the 14 here. 14 minus 5 is 9, right? 3 to the second is 9, so yeah, that worked. All right. In our next example, we have the difference of two logs. Whenever you have more than one logarithmic expression, right? So we got a log of 45x, we have a log of 3. That's two logarithmic expressions. We want to combine them or collapse them into one logarithmic expression. So we're going to use the properties of log here. We're going to subtract. When we subtract, it turns into a quotient, a fraction. Right? So the subtraction becomes a fraction. Okay. Also remember that if you don't see a base, the base is 10. So this is log base 10 of 45x over 3 equals 1. So that means by definition, when we do this definition, it's going to be 10 to the 1 equals 45x over 3. Well, I guess we should reduce it first. So it's going to be 10 to the 1 equals 15x. That's what that is. All right, so just solve for x, divide by 15, and we get 2/3. All right, now we need to check this. We're going to plug this into this expression. All right, so it's 45 times 2/3. Take the log of that, and then subtract log of 3. Well, let's take this first. 2/3 of 45 is 30. And continue with the left side. Right? We're basically doing the same thing we did before. Rewriting the subtraction as a fraction. So 30/3 is log base 10. And remember, if you don't see a base, the base is 10. So this is saying 10 is equal to 10 to the 1. So yeah, that's right. All right, that's it. So that worked. Normally, we want to use properties of logarithms, but you don't want to use the property of logarithm when the exponent is even. An even exponent, because if it's an even exponent, that means you can put a negative value in when you normally cannot put a negative value in a log, right? An even exponent will make it positive. So in this case, I'm not going to do this, right? Usually you can bring down the exponent and it'll make the problem easier. And in fact, the textbook makes this mistake. All right, so yeah, yes, there is a textbook. This example came from the textbook and they did it wrong. So it's a good thing we're avoiding the textbook. Anyway, so here, we're not going to do this, okay? We're just going to go back to this expression and rewrite it using the definition. So it's going to be x squared equals 4 to the 7, right? So 4 to the 7 equals x squared. Now we're going to solve this like normal, right? So we're going to take the square root of both sides. But remember, when we take the square root of both sides, we're going to do plus or minus. So it's plus or minus the square root of 4 to the 7th. Now, this is actually easier to solve by doing the square root first, then dealing with this exponent of 7. All right, so it's plus or minus square root of 4 raised to the 7th power. So square root of 4 is 2, so it's plus or minus 2 raised to the 7th, which makes it plus or minus 128. All right, so both answers are acceptable. Usually, the answers we reject are the ones that make the inside of the log a negative value. But in this case, because it's being squared, both positive and negative are acceptable. And those are our answers. All right, moving on. Oh, here we go. Here's another example of two logarithmic expressions. We're going to combine them using properties of log. Remember, with addition, it turns into multiplication. So we're going to do x times x plus 9. All right, and go ahead and multiply that out. Now we're going to do a rewrite, right? There's a base of 10. Remember, if you don't see a base, the base is 10. So it's going to be x squared plus 9x equals 10 to the 1, which is just 10. So we move the 10 over to the left. Now it's a regular factoring problem. We factor it out, and we get x plus 10 times x minus 1 equals 0. And we get the values x equals negative 10 or x equals 1. Now, this time it's pretty obvious. So I'm not going to do a whole full-blown check. I'm just going to, you can't put negative 10 into this, right? There's no log of negative 10. The domain of logarithms is all positive numbers, okay? So we can't plug in negative 10 either in the first expression or the second expression because negative 10 plus 9 is negative 1. But it only has to fail in one spot. Once it fails in one spot, you can just reject it. So we're going to reject the negative 10. 1 is okay. Log of 1 is 0. Log of 10 is 1. So that works anyways. So that's it. Okay, so just make sure whatever answers you get, don't make the inside of these negative. All right, continuing. And so that was the last example. So we're going to the what's expected. So we're going to be able to solve exponential equations. All right, we'll get lots of practice with that. We'll probably spend a couple days on that, and be able to solve logarithmic equations. We'll probably spend one day on the first one and another day on the second one. No, probably spend one day on both of them and then another day on the second one. The second one actually has a lot more variety. The first one, there's not too much variety. All right, so we'll spend 2 days practicing these. That's it. Good luck.